Hi, this is Dr. Liu. In this video, I have a number of questions to go through as examples. In previous videos, I have introduced kinetic energy, work, and also work kinetic energy theorem, but I didn't really do a lot of examples except for the kinetic energy. So in this video, I'll have a number of examples to go through, and all of these are from University of Physics, published by OpenStax, and chapter number is 7. So we start with 747. Calculate the kinetic energies of a 2,000 kilogram automobile moving at 100 kilometers per hour. Apparently we need to convert this unit into meters per second. And then B, a 80 kilogram runner sprinting at 10 meters per second. And C, a 9.1 times 10 to the minus 31 kilograms. This is the electron's mass. Electron moving at 2.0 times 10 to the 7th meters per second. So that's almost 10% the speed of light. So it's a very fast moving electron, but it has very little mass. All right, so let's start with A. Kinetic energy, or sometimes written as EK, is 1/2 mv squared. So we have 0.5 times 2,000 times the 100. Let's do a conversion. So we have kilometers per hour. And we know that we have 1 hour per 3,600 seconds, and we also have 1 kilometer per 1,000 meters. So this whole conversion gives you 1,000 over 3,600, or 1 over 3.6 conversion factor. Let's put these in parentheses. And we need to square this as well. So kilometer, hour. So this is numerically 100 over 3.6 and then square. So let's calculate this value. This should be in joules. And let's use our Python calculator. So let's move it to the right. We have 0.5 times 2,000 times, so let's do parentheses, 100 times 1,000 divided by 3,600, that is divided by 3.6, close parentheses, and raised to the power 2. So we have this much energy. This is in hundreds of thousands, so 772,000 if I keep two sig figs, 3 sig figs. Let's do that. So 772,000. So 772,000, or 7.72 times 10 to the 5th power joules. We can also write this as 772 kilojoules if we want. Okay, so let's move on to part B. Now we have a human being. Kinetic energy is 1/2 mass velocity squared, so 0.5, 80 kilograms mass, 100 square. So this should be easier to calculate. Just eyeball the numbers. So 100 times 80, so 8,000 times 1/2 is 4,000. Joules, or 4.00, keeping 3 sig figs times 10 to the 3rd power joules, or if you want 4.00 kilojoules, right? So part C, this one has the mass of an electron, extremely small mass, but at very high speed. So 0.5 times 9.1 times 10 to the minus 30, then times 2.0 times 10 to the 7th, and then square this. So this is another opportunity, like before, that I can do a demonstration of how to handle these very big and very small numbers. So we never really type these powers of 10 in calculators. We just calculate them by hand. It's actually easier. So let's do 0.5 times 9.1. So then let's move on to the 2.0 and square. So that's 4.0. Then times 10 to the, we skipped minus 31st, and we also skipped this 10 to the 7th square, that is 10 to the 14th power. So plus a 14. So although we have a very large positive, we still have a very large negative. So the result is going to be very small amount of energy. So, and then we'll just calculate these three numbers together, and then separately calculate the power of 10. Okay, so let's pop up the calculator. 0.5 times 9.1 times 4. So we have 18.2, or 1.82 10 to the first power. So we have 18.2 times 10 to the, so 31 minus 14, that 30 minus 13, so it's 17 negative joules. Or we move the decimal place, 1.82 times 10 to the minus 16 joules. Okay, so except for the very last one, we've calculated the first two in previous examples. Basically, a vehicle lighter in mass than this one, and moving at roughly highway speed, and that will result in hundreds of thousands of joules of kinetic energy. And then the person walking will be hundreds of joules, but this is a sprinter, so there's more kinetic energy to that. And this is an elementary particle, and as you can see, even though the particle moves very fast, almost 10% of speed of light, it still has very little kinetic energy. Alright, so let's move on to the next question. This question is 731, and this one concerns work done. So a constant 20 Newton force pushes a small ball in the direction of the force over a distance of 5.0 meters. So what is the work done by the force? Let's recall work done by the force. This is force, displacement, and then the angle between, cosine of the angle between the force and the displacement. Since the force pushes in the direction of that displacement, this angle is 0, cosine 0 is equal to 1. So we're down to just force times displacement. That's a very basic example. And then we have 20 newtons and multiply by a distance of 5. So we have 100 joules of work done. This is 731. This one is very simple, just one force, and it's work done. The force times its displacement. So let's move on to the next one. This one we have a force that is at an angle with the displacement. The question number is 728. So how much work is done by the boy that's in the front, pulling his sister right in the back, 30.0 meters in a wagon as shown below? Assume no friction acts on the wagon. That's very weird, but let's, for the moment, for simplicity, we'll just assume there's no friction. And from the diagram, we found out the force magnitude was 50 newtons, but it was at an angle 30 degrees, and the displacement 30 meters, also mentioned in the text. So we'll use the same exact formula. So work is done by the boy. So that will be the force from the boy, the displacement pulled, and the cosine angle between the force and the displacement. In this case now we have a 30-degree angle, so it's cosine 30 degrees. And the force is 50 newtons, displacement 30 meters, then times cosine 30 degrees. So we have plenty of space. Let's just move down one line. 5 and 3, that's 1500, and then times sine 30 degrees, 0.866. So let's use our calculator for the final step. So 1500 times 0.866. So we got 1299, about 1300. If you keep the right amount of well, say three sig figs for 28. Okay, let's vanish that. So this is 1299 joules. So we can definitely do an approximation. Everything's two sig figs, but I like to keep 3 sig figs because homework accuracy is 5%. With 3 sig figs, you can definitely get within 5% if your steps are correct. So I'm doing that. That would be 1.30 times 10 to the third power joules, or 1.30 kilojoules if you want. So this gives you a slightly less simple calculation of work done, which is force displacement times cosine of the angle. So let's move on to the next question. Let's make a little bit more space. Okay, I guess by making, okay, here, looks perfect. Okay, so question 725. In this question, we have 3 parts. Part A, calculate the work done on the 1500 kilogram elevator car by its cable to lift it 40.0 meters at constant speed, assuming friction averages 100 newtons. B, what is the work done on the lift by the gravitational force in this process? C, what is the total work done on the lift? Okay, so part A, we're calculating how much work done on the lift by how much work done on this elevator car by the cable. So we need to find out how much force the cable exerts, and we know the displacement is 40 meters. Excuse me. And the cable must be exerting a force along the direction of the elevator car's travel. So there's no need to concern with angles. Angle 0. So let's just draw a small diagram. Let's move it to the right side. I want to keep some space for the left side. So here we have an elevator car. So it's being pulled up by tension, and it's also, let's draw from the center. It's pulled down by gravity or weight, whichever symbol you prefer, and also there's a certain amount of friction, so there's an Fk. Whatever that is probably from some friction of the maybe on the cable and the pulley system. So it accounts for 100 newtons downward. Alright, so in order to, let's write this down, we need to find tension first. So once we have tension, we can multiply tension by 40 meters to get the work done. So we need to find tension, and we're actually, we know that the elevator car is moving at constant speed. So constant speed, that means Constant speed means acceleration is equal to 0, or net force equal to 0, or the upward force minus the downward force is equal to 0. So from this we can calculate tension. Tension is the gravity or weight plus kinetic friction. And the weight, we know the mass is 1500, right? So this is 1500 times gravitational constant 9.8, so that is weight. And friction was given as 100. Alright, so now we found T. So let's pull up our calculator. 1500 times 9.8 plus 100. So we have 14,800. So 14,800. So in newtons, or I'll just write 1.48 times 10 to the 4th power newtons. Okay. So now we have we have tension. We can calculate work done by tension. So let's put a subscript down here to represent work done. And also I do realize that work done and weight, they have the same symbol, but since the text prefers weight with W instead of F sub G, I'll just make note that this is work. This is weight. This is work done by tension. So work done by tension should be tension times displacement, and they're in the same direction, so the cosine is ignored. And 1.48 times 10 to the 4th power is the force. Then the displacement is 40, as stated on the question's text. So I'll just bring out the calculator and recall the last answer, that's an underscore. So then times the 40 meters distance. So now I reach hundreds of thousands, 592,000. So this is 592,000 joules. Or I prefer 5.92 times 10 to the 5th joules. Okay, so now we know part A. Let's move on to part B. Okay, part B, what is the work done by the gravitational force? So that's W. So let's see. W points down with this amount, right? And the displacement is upward, so the angle in between should be 180 degrees. Weight is down, displacement up, right? So let's draw this displacement. I know it's not to scale, but at least we know the direction. So these two are in opposite direction. They have 180 degrees. So let's call this. This is going to be a bit confusing because we're using W on both sides. The left side represents work. The right side represents the weight, the force. So this weight times displacement, cosine angle between weight and displacement. So this is mass gravity. Ooh, okay, so don't have to use W anymore. Then displacement, cosine, because the two are opposite, right? Up, this is down, 180 degrees. Cosine 180 gives you a minus 1. So there's a minus 1500 times 9.8 times 40. So this is almost the same in absolute value as this quantity, because this 100 is pretty small, right? 1500 times 10 is 15,000, and 1 out of 15,000, that's not even 1%. So it seems like the elevator is operating with pretty good efficiency against friction. So let's calculate this quantity here. So 1500 times 9.8 times 40. So we have 588,000, and the other one was 592,000. So 588,000 joules or minus 5.88 times 10 to the 5th power joules. Okay, so let's move on to part C. What is the total work done on a lift? So we did talk about this. Work done, net work done should be one of these two ways: net force, displacement, cosine angle between the net force and the displacement. Right, so this is one way to do it. You net or you sum all the forces, and then you multiply that with displacement and the angle. This looks like an alpha. Let's redo that. That looks better. So this is one way to do it. And as we know, net force is 0 because of constant speed. So it's going to be a 0 times a 40. And there's not going to be an angle because a zero force is a zero length vector. It doesn't have a well-defined direction. So anyway, this is 0. So 0 joules of net work done, because the despite all the forces are doing work, tension is doing positive work, gravity doing negative work, and friction also doing a small amount of negative work. Regardless of all these work, the elevator car did not accelerate, so it didn't increase its kinetic energy. If it stays with a constant speed, its 1/2 mv squared stays unchanged, and there's no increase of kinetic energy in that result. So no increase of kinetic energy, no net work done, because kinetic energy can only be increased if there's a non-zero sum of work. Alright, so we have two more questions. Let's move on to this next one here. This is 755. A constant 10 Newton horizontal force is applied to a 20 kilogram cart at rest on a level floor. Okay, so now we are dealing with horizontal motion. If friction is negligible, okay, what is the speed of a car when it has been pushed 8.0 meters? Okay, so this part involves forces, displacement, masses, and speed. So what we should do is we should use the work kinetic energy theorem, because we could calculate work. We have a force and there's no friction, so this is the only force that will do work. Gravity and normal force, they don't point along the direction of motion. And the force times this displacement gives you how much work is done. That also gives you how much kinetic energy has been increased. So if we just assume the cart starts at rest as it states, then the increase of kinetic energy will be the new kinetic energy minus the old. The old is 0. So let's do this. We use work kinetic energy theorem. So work is increase of kinetic energy. And the left side, the work done is just by one force. So this force times displacement. The angle is 0 degrees. So force times displacement is work. And increase of kinetic energy is 1/2 mv2 squared minus 1/2 mv1 squared. And v1 is equal to 0. Right, so let's do this. 10 Newton force times a displacement of 8 meters equals 1/2 m is basically, this is common factor. I'll factor them out, but it really doesn't matter, but this is still useful if we have a non-zero initial velocity, right? So 0 initial velocity. So this is equal to 0.5 times the mass is 20 times v2 squared. Okay, so the left side is 80 and the right side is 10 times v2 squared. So 80 equals 10 v2 squared. So v2 squared is equal to 8. And v2 is equal to square root of 8. So that's square root of 2 times 4. So 2 root 2. If root 2 is 141, 2 root 2 is 282. Oops. Meters per second. Okay. So in this question, we just applied the most basic form of work kinetic energy theorem. On one side, we have information about the force, the displacement. On the other side, we know the mass, we know the initial speed, so we can find out the final speed. So this is our formula right here. So let's go ahead and do one more question like this. Okay, so this one is 753. Using energy consideration, that is this theorem, calculate the average force a 60 kilogram sprinter exerts backward on the track to accelerate from 2 meters per second to 8 meters per second in a distance of 25 meters. If he encounters a headwind that exerts an average force of 30 newtons against him, so the wind is blowing against him, and that gives an effective resistance. So this sprinter exerts a backward force on the track. Basically, according to Newton's third law, the track exerts exactly the same amount of force against the sprinter to accelerate the sprinter forward, and this is the force we want to consider that does work to the sprinter in order to accelerate the sprinter from 2 meters per second to 8. So here's the force from the track. Let's actually use this force on the sprinter by the track. So that is the same as force on the track by the sprinter. Alright, so we'll do a very simple free body diagram to analyze the forces. So here's our sprinter, just a box. And here's the force. So on the sprinter by track, and here's some friction. We also have gravity, normal force, that they don't really do any work. They're perpendicular to the direction of travel. The direction of travel is this way, it's forward. Let's put a arrow sign here. So that's displacement to the right. So in order to use work kinetic energy theorem, the left side will have to include the network. That means the net force times displacement, right? So we still use work kinetic energy theorem, except that the network is work done by net force. So sprinter over the on the sprinter by the track, and minus kinetic friction. So this is net force, right? This is net force. This is force net. And times the displacement. And apparently the net force will be pointing to the right along the direction of displacement. So cosine 0, that's equal to 1. We'll skip that part. And now we have 1/2 m v2 squared minus 1/2 m v1 squared. We have an initial velocity of 2, so it's not 0, right? It's not always 0. So let's put numbers into both sides of the equation. We have force on sprinter by track minus kinetic friction is well, not kinetic friction. The headwind is 30 newtons of force times the displacement of 25 meters is equal to 1/2 m. And factor it out at 1/2 m, so we have v2 squared minus v1 squared. That's 8 squared minus 2 squared. We can get the right hand side done first. Okay, so I forgot to put in the mass, but that's okay. 60 kilogram times 1/2 is 30 times 8 squared is 64, and 2 squared is 4, so 60. That is 1800 joules. Okay, so that means our force on sprinter by track minus 30 is equal to 1800 divided by the 25. So here's that 25 distance. Okay, so divide by 25 is like divided by 100 and times the 4, right? So divide by 100, you move your decimal place 2 times, times 4. So 18 times 4, 36, 72. So we have 72. And that is in newtons, by the way. But let's hold on. So force on sprinter by the track is equal to 72 plus 30. So the 102. Now we can put the newton into the final answer. So 102 newtons. All right. So this question is a bit more convoluted compared to the straightforward work kinetic energy theorem, because this one involves 2 separate forces opposing each other, and it also involves 2 kinetic energies. Neither of them has a 0 speed, so neither of them is 0, and we have to consider them both. So the increase of kinetic energy is entirely due to the net force done doing work. All right, thank you.